So thank you for the introduction and thank you for your invitation. Welcome to the International CAN Conference here in Paris. So on the previous CAN conference, the new CAN-FD protocol has been presented to you. Meanwhile, some OEMs are already working on the serious introduction of CAN-FD. So does our company, and that's why I would like to present you CAN-FD from the viewpoint of an OEM. So here you can see a short outline of my talk. In the first part of my presentation, I will show you why CAN-FD is an interesting technology for us. The second part then will deal with the physical limitations you have in your vehicles. And finally, in the third part, I will compare different concepts for the usage of CAN-FD in the grown vehicle electronic architectures. As an introduction, I have here for you the development of networking key figures over a time scale of approximately the last 25 years. So Daimler was among the very first adapters of CAN technology. The first passenger car that used CAN was the S-Class, released in 1991. And only 1 year later, CAN showed up in a truck. So even in the era before CAN here, there were ECUs inside the vehicles and there was an exchange of data on a very small scale. But with the introduction of CAN here, the number of ECUs, buses and signals started to grow rapidly. This growth seems to have slowed down a little bit in recent times here. However, this is due to the fact that there is a trend for higher integration. This means the single ECUs perform more functionality, they are more powerful, and the respective signals are larger in size and more complex. And this development goes along with an exponentially growing demand for bandwidth. So in these days here, we used to call 125 kilobits high-speed CAN. And for instance, in the new S-Class here that was released this year, we had to introduce FlexRay to cope with the demand for bandwidth. So from this slide, you can already see all data buses are required to become faster in future. Now, I would like to take a closer look at the EE architecture of these two vehicles. So here on the left-hand side, you see a state-of-the-art architecture of the new Actros truck. And on the right-hand side, you can see the architecture of the S-Class that was released this year. So generally, architectures like these are divided into different domains like powertrain, chassis, body, and so on. And there is a centralized gateway in both architectures that is interconnecting these domains and that provides the necessary routing of information between the domains. Most bus systems used today are CAN and LIN, and in the passenger car we have here a FlexRay bus in the chassis domain. So for future developments, these kinds of architectures are facing some limitations. The first limitation are the centralized gateway devices. They come to the limits in terms of routing capacity. And the other limit is the bus load and all these subdomains that is growing and reaching a critical limit. So future architectures will look different. And here I have brought to you a draft of such a future architecture. So it's really just a draft. The architecture that will go into production many years from now will definitely look different in many details. However, you can see some trends from this slide. First of all, we still will have a division of the architecture into several domains, for instance, body, chassis, powertrain, and so on. And the most striking difference now is that the centralized gateway will be replaced by an Ethernet backbone structure here. And this Ethernet backbone structure is then interconnecting several domain controllers. Now, Ethernet is a very fast bus system that works with a comparatively large payload, and this will have its impact on the sub-buses of the networks as well. So first of all, there will be new message handling and routing mechanisms. There will be a trend for larger payload and a trend for more bandwidth. What does that mean for CAN now? So first of all, if you look at this picture and count the number of interfaces, you will see that CAN will continue to play an important role in future vehicle architectures. So the red lines are CAN or maybe CAN-FD, and there are quite a lot of CAN nodes inside. If we look at the bandwidth, classic CAN will not provide enough bandwidth anymore. However, from our estimations, CAN-FD could have enough bandwidth for approximately the next 1 or 2 vehicle generations. And finally, the trend towards larger payload can be addressed very well by CAN-FD and its ability to handle up to 64 bytes of data. Now, on this slide, I would like to compare the classic automotive field bus systems CAN, CAN-FD, and FlexRay. I did not include Ethernet here because it's not a real field bus, it's a switched network. So first of all, CAN-FD will give us more bandwidth than classic CAN. However, it's also clear that FlexRay will continue to be the fastest field bus systems in the market. CAN-FD will bring us additional royalties for the devices. However, also FlexRay has additional expenses that are especially due to the physical layer hardware. CAN and also FlexRay it's possible to build large topologies with large extent. If you're doing this with FlexRay, you need an active star. And CAN-FD also has the ability to build large topologies if you do not go to the limits in terms of your baud rate. So if you really want the fastest baud rate with CAN-FD, your topology has to shrink. We think that CAN-FD is a very flexible system because it's as easy to handle as the classic CAN. It gives you more bandwidth and more payload. The problem with FlexRay is that you have to fix your entire communication schedule in advance, and a subsequent change to this communication schedule is a very difficult thing. In terms of hardware availability, we see some very promising announcement of the semiconductor manufacturers for the high-end microcontrollers. However, we also see a significant lack in low-end microcontrollers. So think about a powertrain network using CAN-FD. You need a high-end micro for your gear controller, for your engine controller, but you also have some simple sensors or some simple actuators in there. And there is no point in putting in a 32-bit multi-core micro in these devices. So we still need some low-end micros that are cheap and small in size. And finally, of course, CAN-FD has the potential to increase the flashing speed on CAN networks. Now this slide here shows the relationships of communication speed and data throughput of CAN-FD. Here on the horizontal axis, I plotted the bit rate in the data phase. And here on the vertical axis, you can read the average bit rate you get. And this average bit rate value can be compared directly to the bit rates of today's CAN. So the first two graphs compare different arbitration speeds and different identifier length. And the third graph here on the right compares the influence of the extended payload. And from these graphs, you can learn 4 things. First of all, the average baud rate of CAN-FD goes into saturation for high bit rates in the data phase. The second thing is, if you're looking at overall high performance, you must not neglect arbitration speed. For really fast CAN systems, you also have to use fast arbitration speeds. Then, of course, CAN-FD is more effective if it's combined with the 11-bit identifiers. And finally, it's most effective if it's being used with large payloads of 64 bytes, especially if you combine that with high bit rates in the data phase. So for the beginning, we think of using CAN-FD with baud rates of 500 kilobits for arbitration and 2 megabits for the data phase. And this would give us approximately, or will approximately double our average bit rate if we would stay with 8 bytes in payload. If we would go to 64 bytes, we would have the chance to reach a factor of 3.5 in the best case. Now, the goal is to bring CAN-FD into our topologies and to make the topologies work over the entire lifetime of a vehicle under any circumstance. And of course, we want to have the highest baud rate possible in that case. And here on this slide, you can see how to safeguard such a network. So in the beginning, you have your ECUs in your vehicle, and that gives you the structure of your topology and the transmission line length. You can treat this by means of measurement or by means of simulation. And in the end, the result are delay and symmetry values for all the communication relationships in here. And this is only the typical case. Now you have to take into account the worst case, especially the worst case characteristics of your transceiver, and your clock sources are important. These things you can get from data sheets or from the device suppliers. But you also have to consider things like temperature effects or jitter that is imposed by electromagnetic irradiation. And these values are generally experience values. Then it's also wise to have some safety margin, for instance, for future extensions. And now, with all these things, you have all your basic conditions to do the calculation of your network, and you can apply these to the limiting principles of the CAN protocol. So there are protocol limitations for arbitration phase. They apply to CAN and CAN-FD. And there are limitations for the data phase that apply only to CAN-FD. So during this conference, the colleagues from Bosch will give you a detailed mathematic relationships of these protocol limitations you need to do this calculation. And in the end, you will find the highest data rate you can use safely in a network. We already did a lot of such estimations and measurements. And here in this table, I would show you typical communication speeds that could be used. So please note, if you build up these topologies in your laboratory or on your table, you test it, you will find that it works with data rates twice the speed I've given you here. But this table already takes into account all the worst case effects you need to be safe in a mass production of a CAN product. So the first topology is the point-to-point link, the simplest CAN topology possible. The only limiting factor is bus length, and if you just have a few meters, you might go up to 1 megabit for arbitration and 4 megabit for the FD data speed. This topology can be increased by adding several nodes here, strictly avoiding stubs. By the way, this kind of topology is frequently used in FlexRay networks. So these mid nodes, they deteriorate your signal quality, and that's why you have to go down a little bit in the FD data speed. The most frequently used topology in CAN is the bus with stubs. You will find that in any CAN teaching book. And the main limitations are the number of stubs and the length of the stubs. And these stubs, they cause reflections, and that's why you have to go down in arbitration speed and also in the FD data speed. So typically we use 500 kilobits here. In special networks you can also go up to 667 kilobits, and FD data speed is approximately 2 megabits in maximum. For very large topologies you might have to go down to 1 megabit. Another possibility are star networks with ferrites. So this used to be a Daimler patent. The main limiting values are the overall transmission lines and the number of nodes. And in terms of baud rate, you can approximately achieve the same values as with a bus with stubs. And this kind of topology has advantages if you have networks that have a lot of variations. Finally, some fellows like to save the ferrites and build star topologies without ferrites, but the signals start to look very awful quickly, so I would not recommend this for higher bit rates. So now I've been talking a lot about principal characteristics of the CAN-FD protocol, about physical layer and hardware, but you have to look at the whole process for the integration of CAN-FD into the electronic architectures. So the first steps are relatively simple. You have to get your hardware into your ECU, which means a CAN-FD capable microcontroller, and you have to make your physical layer network work with a proper baud rate. And then you have to integrate CAN-FD into the ECU standard software, which means you have to enable the software to interface to the CAN-FD IP and to work with a larger payload. And what is even more important are the mechanisms for routing and message handling. And finally, if your application can benefit from larger payloads, you also have to adopt your applications. So here on the right side, you see a software development model that we use for the development of our ECU software. It's the so-called AUTOSAR model. And I don't want to go too deep into detail here, but I just want to show you the yellow highlighted parts are the parts of the software stack that are most affected by the introduction of CAN-FD. You may also have to adapt your applications if necessary, and you must not forget all your tools and your generators that are used for the maintenance and the development of the software. They also have to be adopted. A very decisive part of the integration is the choice of the right routing and message handling mechanisms here. And for that, I would like to compare different concepts, how you could do that. So the first possibility I just called CAN-FD 8, which means you have just one PDU that is 8 bytes or less. So in this context, the term PDU means protocol data unit, and this is nothing else but the bare payload of an application without any additional control information. So this case is in principle nothing else but what we are doing today with CAN, only that it's faster. So it has no impact on the application, it has no impact on the routing mechanisms, but you cannot profit from larger payload and you are limited in your growth in bandwidth. The next possibility would be to enlarge this CAN frame and to use up to 64 bytes. However, only with one PDU. This is really suitable if you have applications that can benefit from these large PDUs. But in this solution, has an impact on the entire software stack up to the application layer. So you have to do a lot of changes when you introduce that. And what is even worse, the routing mechanisms here, for instance, from CAN 2.0 to CAN FD, cannot be performed automatically because the relationship between this PDU and these smaller CAN 2.0 PDUs is very complex. So you would have to do a routing on an application layer, and this is very ineffective and resource consuming. To improve this, you could go back to the 8-byte PDUs and arrange several of these statically in one large CAN FD frame. So you have the same PDUs like today. This has no impact on the applications, only on the lower software stacks. And because now the relation between these frames and the PDUs are clear, you can apply an automatic routing mechanism again. However, this concept also has two major drawbacks. So in the first, if you have one single bit changing in one of these CAN 2.0 PDUs, this means on the CAN FD network, you have to transmit the entire frame with all PDUs inside. And if you have a lot of spontaneous messages on your network, this will blow up your bandwidth on this bus. So it will use the bus ineffectively. And a second problem is what happens if one of your CAN 2.0 messages during routing is missing or is delayed. So then your CAN FD message will be delayed. So this concept might be useful for systems that are using strictly cyclic CAN communication, for instance in the trucks, but it's not so useful for passenger cars. And so Daimler made up another concept. Here several PDUs are dynamically combined into large CAN frames during the runtime of the system, and they are marked with PDU headers. So first of all, our CAN FD frame, maybe 64 bytes, is nothing else but a container. And inside this container, we have PDU headers followed by the PDUs. And for these PDU headers, we suggest to use 24 bits as a PDU identifier and an 8-bit PDU data length code. So this concept has several advantages now. First of all, you can really use your frames effectively. So you just put in during the runtime what you need to update or to change, and you leave away everything that does not change, which means you have less redundancy, less bus load, and less delay in your network. Then another very interesting topic is, in the beginning I've been talking about the introduction of Ethernet. A very similar solution for this is under discussion for Ethernet networks. And now we have the chance to apply the same routing and message handling mechanisms for Ethernet and for CAN FD. Again, we can do an automatic routing process between CAN FD and CAN 2.0. And finally, if necessary, you can also use PDUs larger than 8 bytes, as long as you do not have to route them to a network that is limited in terms of the payload. So the only disadvantage of that concept is that you have a loss in bandwidth due to the PDU headers, because these are now part of the message field. However, today we frequently use 29-bit IDs to address all the signals, and now in this concept, the addressing is done by the PDU headers, so you might cut the 29-bit IDs down to an 11-bit identifier, and you can compensate the PDU headers partly. So if you would make a greenfield approach to use CAN FD, you might find a better solution than this one. We cannot do a greenfield approach. We have to get it into a grown structure of systems, and we think this is a very effective manner to do so. So let me come to a final conclusion. CAN FD is from our point of view, an important technology to design cost-optimized and flexible future architectures. For the beginning, we think that we could use 2 megabits as a data rate in the data field. CAN-FT is perfectly in line with the introduction of Ethernet. Because it has more bandwidth and more payload, we could now use the same routing and message handling mechanisms for CAN-FT and Ethernet in parallel. And finally, to make the most of CAN-FT, we suggest to use it in combination with flexible PDU headers. Thank you very much.